CBT Nuggets JNCIA Series, Introduction to Junos IPv6. Well, I want to finish up this JNCIA series with kind of a value add. You're probably not going to get very many questions on the exam about IPv6. If anything, it'll be basically just identifying the INET6 family. But I want to make sure that you have this foundation because IPv6 is here now. Okay, we've depleted the IPv4 addresses, and this is going to be in your very near future, whether you go into your imaginary Nugget Lab environment or in your own real-world scenario. So I want you to have a kind of a nice foundation of IPv6. This is by no means an exhaustive look at IPv6, but it will give you a nice head start if you aren't familiar with it already. So in this nugget, we're going to look at the IPv6 distinctives. We'll also look at the addressing structure of the 120-bit IPv6 address. We'll look at different address types and features. We'll look at IPv6 headers and the extensions. Talk about neighbor discovery, and then finally we'll go on our Juniper router and configure an interface with an IPv6 address. Sound good? All right, let's dive in. Okay, so everything we've been doing through this entire JNCIA series has been dealing with IP version 4 addressing. Now, you may have learned this when you use the resources that I showed you early on, or maybe you've done your own research on IP addressing and subnetting, but we know that the IPv4 address space is a 32-bit address space, right? The source address, destination address field is really just 32 zeros and ones. And we have, based on that, about 4.2 billion addresses available. Now you might think, wow, that's a lot of addresses. And that's what the people that actually designed the TCP/IP stack thought as well. They weren't thinking about YouTube or the World Wide Web when they did this. And if you realize that, we need more than one IP address per individual in all these big countries, United States, Brazil, China, India, we have more than one device per person. We have a bunch of computers and personal devices, and we use IP addresses for other uses as well. This 4.2 billion space is not enough. Okay, it's not going to meet our needs. And actually, this is 2012. Well, officially in 2011, according to the IANA, which is the organization responsible for this pool, that IPv4 free pool, well, it's used up, okay? Now, exhausting the IPv4 pool sounds kind of scary, but when we think about it, we've got some pretty good mechanisms in place to help us accommodate this, okay? So if this goes up to the internet here, here's my router. I know that I could use network address translation. I can use back here in my corporate network or over here in my DMZ, I know I can use RFC, request for comment, 1918 addressing, or I can use the private IP addressing space of IPv4. As a matter of fact, here is the official RFC 1918, and you can scroll down here and you can see that address space, which I'm sure you already learned about. Okay, 10.0.0.0 through 10.255.255.255 or 10/8. We've also got 172.16.0.0 through 172.31.255.255 or 172.16/12. And then, of course, the 192.168.0.0/16. And this is the one you probably use right now at home behind your DSL modem, your cable modem / router, whatever you're using, probably 192.168.1.0. Okay, so inside of our organizations we can use this, and then we can just translate to some public IP address. So corporations can use, let's say, a 10.10/16 network or 172.31/16 network, and then they can translate to real addresses that they get from service providers, from IANA, something like 209.200.165.30/ and we can even take this NAT and we can overload it, okay, and we can do what's called port address translation, where we can take this entire space back here and overload one single address and just use port numbers. So it can be 165.30 and then port numbers, so colon 2000, 2001, 2002, and so on, and we have a table on our router that keeps track of that on behalf of our inside host. So we've got some great mechanisms, some great workarounds to keep us going with IPv4 for quite a bit of time. And as a matter of fact, it's network address translation itself that is going to be one of those protocols that helps us transition. Okay, we can use various NAT technologies like NAT DS Lite and NAT 64 and NAT 444. We've got other flavors of NAT that are going to help us transition from IP version 4 into IP version 6. Now, if you want to find out more about kind of the theory and the design and the big picture, there are a couple of websites I can point you to if you want to do a web safari once this nugget is done. You can go up to juniper.com and you could actually just do a search for 2000360. It's a white paper, Tools and Strategies for Coping with IPv4 Address Depletion. Pretty cool article. It's only 12 pages long, and it'll talk about a lot of the transition mechanisms, and it gives you some very good case studies. You can even go deeper with this particular site right here, and you can see that's basically juniper.net/us/en/company innovation IPv6, and you can find out more about the challenge that we're dealing with. A little movie up here, and you can get down into some nitty-gritty and learn more about coexistence and transition. This is good design documentation and good enterprise documentation. Now, none of this is actually going to be on the JNCIA exam. Okay, you will not have a single IPv6 question on this exam. This nugget is a value add, but I feel like, and I know from experience, that this is a very important topic, and I want you, you're probably relatively new in switching and routing. I don't want you to put this off, okay? Because it's, I remember being a kid in elementary school and they kept saying, hey, we're going to the metric system. We're going to the metric system. Got to learn the metric system. Well, I'm still pouring out, 8 cups of this and a half cup of this, and you know what I'm saying? So what I'm telling you is it's not going to be that far away, okay? IPv6 is already here now, and it's moving from the service provider into the enterprise, so you want to get on that track. Okay, so IPv4 and IPv6 are incompatible. We have to know that. That's why we need transition strategies and coexistence strategies. But they're also incompatible as far as their IP addressing scheme, because we know that IPv4 is basically a string of 32 binary zeros and ones. Well, that's 2 to the 32nd power, right? Well, IPv6 is a string of 128 zeros and ones, which gives us 2 to the 128th power possibilities, which is just some astronomical number that's not even worth even documenting, okay? So it's huge. Now we know that we can take an IPv4 string of zeros and ones and represent it in a dotted decimal format, like 192.168.100.1. And we know that of these 32 bits, we've got 8 bits here for the first octet, 8 bits here for the second octet, 8 bits here for the third octet, and 8 bits here for the final octet. So for example, this .1 is really 000000001, right? You might think, well, why don't we just go ahead and take the 128 bits and make that dotted decimal? No, couldn't do it, okay? I mean, it would look like, here's my IPv6 address. It's 32.1.15.185.0.0.0.0.0. You with me? It's ridiculous, okay? So we can't do that. So what we have to do is we have to break this up into 8 16-bit binary sections. So 8 16-bit binary sections which are represented in hexadecimal format. And so being able to convert from hexadecimal, from binary to hex and hex to decimal would probably be a good thing to learn eventually, but for our sake, we're not going to cover it here in this course. But let me give you an example. Okay, so like I said, your IPv6 address is really 8 of these, right? 8 of these 16-bit fields. So of course, 16 times 8 equals 128, right? So we break these up into 8 boxes, okay, 8 sections. But then we take these sections and we then represent them by taking these 4 bits and going here, taking these 4 bits and going here, these 4 bits here, and these 4 bits go here. Then we represent each one of these 4 bits by its hexadecimal representation. So these, of course, all 4 zeros are going to be 0. 1101, which in decimal is 13, is represented in hex by the letter D. 1011, which is actually 11 in decimal, represented by B in hexadecimal, and then 1001, which is decimal 9, represented by hex 9. So these 16 zeros and ones become this little hex segment. And so 0DB9 is a segment, and we separate these with colons, okay? And what we find is a lot of these addresses end up having a bunch of segments that actually are all zeros, okay? Where all 4 hex numbers are all 16 bits are all zeros. So let's say we had one of those situations. If that's the case, we have a feature called zero suppression. Remember, all 8 segments consist of 16 bits, so we can remove leading zeros from each section. So for example, if this section is 0DB9, we could represent this section, like here's a colon, as just simple DB9, and then put a colon here. Why? Because the system knows that this is really going to be 4 hex numbers, but we can get rid of the leading zeros. Something else we can do is that if you have all zeros in your segment, okay, instead of being 0DB9, if it were 0000, you can actually represent that as just colon 0, okay? Now, what if you have a bunch of those colon zeros together? You can compress it even more to just put in there colon colon. So is this a legit IPv6 address? Yes, it's got 1, 2, 3, 4, 5, 6, 7, 8 16-bit segments represented as 4 hex characters, right? Well, we can compress this. Okay, we can't compress 2001. Okay, can't compress that. So put a colon there. Can we compress this? Yeah, we can get rid of the leading 0. So that can just be DB9, right? Then what can we do? Well, one time in the address, okay, one time and one time only in this address, we can say we have 1, 2, 3, 4, 5, a string of 5 0 segments. So we have a double colon together. And we can only do this once, this double colon. And that just basically says a number of at least 2 all 0 segments. And then what do we have here? We have 3 leading zeros, so we can get rid of those and just say 1. Well, you might say, well, okay, this double colon, how do we know how many segments of zeros that are there? Well, it's easy, because we have 1 segment here, we have 1 segment here, and 1 segment here. So the system knows that there's 8 segments, right? Well, this has to represent 5 segments of zeros, because 8 minus 3 is 5, and that's exactly right. 1, 2, 3, 4, 5 segments of 0. So we can represent this IPv6 128-bit address as 2001 colon DB9 colon 1. Pretty cool, huh? Now, do most addresses have this many contiguous 0 segments in them? No, but that's the rules, and it's good to know the compression rules. Now, just like we can use this CIDR representation of the prefix to get a hierarchical IPv4 structure, for example, 10/8, 172.16/16, or down here, 209.165.200.1/30, we know that this prefix represents how many bits are on the network, right? So we can see here the first 8 bits represent the network, the remaining bits are the host on that network. The first 16 bits of the network here, the first 24 bits of the network here, the first 30 bits of the network here. We can do the same thing with IPv6. It's hierarchical. So we could have this address, which by the way could also be represented this way. You could just do 0, 0, 0, 0, 0. You could put 5 individual zeros separated by colons, or like we said, we can take these 5 zeros and put a double colon here, but you can only use the double colon one time in the address, right? Because otherwise it doesn't really know what to subtract from. Now notice we have a /64. So what this is saying is the first 64 bits are the network portion. Well, we know this is 16 bits, right? Well, 16 times 1 times 4, so these first 4 segments are the network. So this is basically network 2001 0db9 0000 0000/64. That would be the network prefix address. And by the way, you could represent it this way. So this address 2001 db9::1/64 is on this network 2001 db9::/64. And we know that this : here really represents 2 segments of zeros, right? 2 segments of zeros, because this is a 64-bit network. In other words, 16 bits, 16 bits, and each one of these colons represents 16 bits for a total of 64 bits. Now we also classify IPv6 categories into the way that they're used. There's really 3 types. Now in IPv4, we have things like unicast addresses, which are basically point-to-point, identifying a single interface or a single endpoint, one client to one server, a unicast address, my laptop to my default gateway, for example, or my laptop to my DHCP server. We also have multicast addresses, which identifies a group of interfaces. Typically they belong to different nodes, but we can send them to multicast addresses for video and audio streaming and things like that, or multicast for OSPF or ISIS or RIP version 2. And of course we have the broadcast. We know that the broadcast, for example, on this network right here, 209.165.200.1 is actually .3. Okay, because .0 is the subnetwork /30. We've only got 2 valid addresses, .1 and .2, so .3 is the directed broadcast on this network. However, in IPv6 we do not have broadcasting. Okay, we use multicasting to do all of our broadcasting. So let's just remind ourselves, what are the 3 types of IPv6 addresses? Now, remember, with IPv6, this address, just like with IPv4, its goal is to identify an interface, okay, or a group of interfaces. That's really what we're talking about here. Now, it just so happens that this interface can be attached to a whole heck of a lot more than a workstation or a laptop. It could be a refrigerator. It could be a microwave. It could be I suppose it could be a lawnmower, all right? So we want to look at the different types of interfaces that can be represented. Okay, so we have, first of all, the unicast address. This is basically a single interface. So a unicast transmission would be from a client, right, to a server, like let's say a web server. So the packets are actually sent to a specific interface on this web server. The multicast address is very important because we no longer have broadcast addresses. So no BC, no broadcast addresses in IPv6. We basically use multicast to provide that functionality. So basically we're identifying a group of interfaces with a multicast address, and typically they're in different networks or different nodes. And our packets are delivered to all of the group members of the multicast group, even if they're in different networks or different nodes. Then of course we have the anycast, and this is not actually that much in use right now. Anycast is also a group of interfaces, but it just happens to be we're going to send the packet to the nearest interface in that anycast group. So for example, if I have a host here, I might want to send a message to a DHCP server or a query to a DNS server. I could have multiple DNS servers in an anycast group, multiple DHCP servers in an Anycast group, and I could be sending it basically to the nearest one. Nearest one in terms of cost, not necessarily, geographically. The one that has the least impact on my network. And something else that's interesting about Anycast is that this interface in this DHCP server, it can have multiple IP addresses associated to it. It could have a unicast address associated to it. It could have an Anycast address associated to it, depending upon why we're using it. Now, something else about our bits here. As we can see right here, this is our 1, 2, 3, 4, 5, 6, 7, 8 segments of 16 bits are 128 bits. The high order, or the leftmost bits, they help determine not just the prefix or the network that we're on, the major network, but they also identify the type. And over here on our table, we can see some specific address types, and based on the high order bits, we can identify it. Now, a couple of these are pretty interesting. If it's all zeros, all 128 bits, which is basically ::/128, that's an unspecified address. The loopback address, which we know in IPv4, or if you don't know, it's 128.0.0.1, that's the IPv4 loopback address, which is really a bummer because they used up an entire, basically, Class A network just for this loopback address. It was a total waste. Well, they didn't make that mistake in IPv6. For the loopback address, it's basically just all zeros with 1 at the end. Okay, you can see that right here. ::1/128. Then we have the link local unicast, which is the closest thing we have to an IPv4 unicast address. That's going to start with FE80, and that's something you probably would want to know going forward, that FE80, the first 16 bits, or the first 4 hex identifiers, is a link local unicast, and FF00 is going to be a multicast address. FF00 then ::/8. Now, unicast addresses are the most common type of IPv6 address, just like with IP version 4. And since we have so many in IPv6, you shouldn't be surprised that pretty much every machine on your network will have at least one global unicast address assigned to each interface. So that's what we have down here in the last row, okay, where it says global unicast is basically all other addresses. So what that means is all of the IPv6 address space that's not currently specified for some other purpose is reserved to be used as a global unicast address. And for now, all the global unicast addresses are going to begin with 2000::/3 prefix. So basically, we have this first 48 bits is our global routing prefix, and technically minus the first 3 bits, but we'll just keep it simple. These first 48 bits are the prefix, and then you've got 16 bits, which is just one segment, okay, for your subnet identifier. So a particular link or local area network within your site, or within your campus, or within your network. And then we had the remaining 64 bits, which is the interface ID. Interesting. Okay, IPv6 has a packet header just like IPv4 does. There's been some major improvements made to the IPv6 packet header. It's been simplified somewhat, and we've removed some things that were security vulnerabilities in IP version 4. Things like the IP options field, for example. What we have here, though, is we have the version field, and that's basically going to be a 4-bit field representing the IP version number. So we know here it's going to be version 6. So if it's 4 bits, it's going to be 0110 for 6. The traffic class is 8 bits long, and this is used to mark packets for the kind of things we learned about in the class of service nugget earlier on, okay? So it's like the IP version 4 precedence and type of service. So this is basically the IPv6 class of service or quality of service. That's what those bits are for. The flow label is experimental. exp, so we'll just bypass that. The payload length, this is going to specify the entire payload length. Everything that follows this header in the packet. This field is 16 bits long, and then we have next header. This is an 8-bit selector which uses the same values as IPv4 to identify the type of header that immediately follows the IPv6 header. Now what we can see down here is kind of the typical default behavior is to say, okay, here's the IPv6 header. The next header field, which is right here, says, okay, the next header is the upper layer header, like for example, UDP or TCP, and then the data. Well, the next header could also be an IPv6 extension header, and these are really cool that these have replaced the IP options. So these extension headers, you can place more than one extension header after the IPv6 header, but then before the upper layer header and data. Okay, and of course here's our source destination address. These are 128-bit fields. We've already talked about that in great length. Let's talk about these extension headers though, because this adds a lot of extra functionality to IPv6, and it's pretty fascinating. The hop by hop options extension header, which could be, let's say, right here, is used to carry data that has to be examined by all routers along the packet's paths. The destination options, just like it says, carries information meant for the packet's destination node. The routing extension header is basically going to provide some of the same things we had with IP version 4. It designates one or more intermediate nodes or router hops that have to be included in the packet's path from source to destination. So we can actually kind of dictate the path that it takes. The fragment extension header is there. This is actually going to be pretty rare in IP version 6. Then we have the authentication header and the ESP header. And if you're familiar with this, these are the two protocols of IPsec. Okay? Authentication header, which provides integrity and authenticity, and then encapsulation security payload, ESP, which provides confidentiality, integrity, authenticity, and they both provide anti-replay protection. So what this tells us is that IPsec is built into IPv6 now. Pretty cool. All right. Something else to know about IPv6, there is no more ARP. Okay. We don't have the ARP resolution protocol anymore. Most everything that was done with ARP is now done with ICMP v6. Okay, let's talk about neighbor discovery, which is a really important feature that improves upon ARP. Like we said, going away. It also improves ICMP. It adds router discovery, and it does some of the things that we did with ICMP redirects. So it combines all of those things and some new features. It's a very important thing. We want to learn that before we actually go in and configure IPv6 on our router. Okay, so we've learned that IPv6 is going to have in the extension headers IPsec AH and IPsec ESP built in. We've also determined that IPv6 neighbor discovery gets rid of ARP. It also improves upon ICMP. We have ICMP v6 as well as other features. One of those features or functionalities is what's called router discovery. Here, our router is going to send out router advertisement messages periodically to announce things like their presence, like a hello packet. It'll also advertise prefixes that it has on its link. It'll help configure addresses. It'll also share information about its links, like the MTU and the hop limit. We also have neighbor discovery, where IPv6 nodes will communicate their link layer addresses, which again are the IPv6 local addresses, to one another, and they use a neighbor solicitation and neighbor advertisement message. This also helps us to find out if we have any duplicate addresses, which should be a lot less common with IPv6, but it also helps us to test the reachability between our neighbors. We also have neighbor unreachability detection. An IPv6 node has to get a positive confirmation of packet delivery, kind of like TCP. How do we do this? Well, one way is that the nodes are going to listen for any new acknowledgments that are coming back, or for similar upper layer protocol confirmation that the packets that were sent to a neighbor are actually getting there. That's the second method. If there's no confirmation, then the node will send a unicast neighbor solicitation message to confirm any next hop reachability. And then finally we have redirects, which are a lot like what we had with the ICMP redirects. Routers use this to inform other hosts on their links that there's a better hop for a particular destination. This allows the router to help our endpoints make the most effective, the most efficient local routing decisions that they can. Okay, let's configure a real simple example here. We're just going to configure a IPv6 address on the loopback interface of this J2320. So let's go ahead and get into configuration mode. We're going to edit interfaces loopback 0 unit 0. Let's set the family, and so far we know it's been INET, but now it's going to be family INET 6. On the exam, don't be fooled. It's not going to be INET.6 or INET v6, anything like that. It's INET 6. And then the address we want to add to this, we'll say is 2001 colon, we could say 0 dB. I don't have to use uppercase, by the way. I represent my IPv6 addresses in all uppercase letters, but it's not case sensitive. So I can say 0 dB9, right? Or as I know, I could get rid of the leading 0 and just say dB9. I can do that, or like I said, I can do uppercase if I want to do uppercase. Okay? But I'll just do dB9. Then I know I could put a colon in here, and I could put 5 more zeros separated by colons. So I could say 0 colon 0 colon 0 colon 0 colon, one more, and then I could put 1, that's the actual address, and then /128 is the actual interface address, and that's just like saying /32 to identify a particular IP address. Now I don't have to put all those zeros in there. I know that one time I can do a double colon, right? So I could say db9 colon colon and then put in the 1 and then 128. Then I can go to the top and let's do a edit interfaces loopback 0 and do a show command. And we can see here's my 2 addresses I've assigned to the loopback address in the 2320. Okay, it's still unit 0, but I've got a family INET or IPv4, and there's my address of 192.168.1.1/32, and then here's family INET 6 with my address of 2001 colon db9 colon colon 1/128. Okay, simple as that. Now obviously to explore more about the local IPv6 addressing you're going to have, and usually you're not going to be statically assigning IPv6 addresses to your Linux boxes, your Vista, your Windows 7 workstations, and all that stuff. That's going to be done pretty much at a higher aggregate level in your network. And again, to learn more about that, go ahead and use all those resources I pointed you to, and you would like to, along the way, kind of keep adding to your IPv6 knowledge, because it's very likely on the on-the-job environment, when you go in there for your interview, make sure that you not only tell them about your experience on the Juniper router, but also tell them that you have worked with IP version 6 and understand IP version 6. It can only help in that interview process. Well, all right, in this final nugget of the JNCIA series, we got an introduction to Junos IP version 6. We covered some IPv6 distinctives and characteristics. We looked at the addressing structure of that 120-bit address. We talked about different address types. Looked at the IPv6 header and the header extensions, talked about neighbor discovery, and then we configured the loopback interface on our 2320 with family INET 6 with an IPv6 address. Well, that concludes the JNCIA Nugget series. On behalf of everybody at CBT Nuggets, the entire team, and myself, Michael Shannon, I want to thank you so much for choosing us as your training solution. And I hope for you all the success in the world, not just in your IT future or your Juniper future, but also life in general. Take care, and once again, thank you and all the best.